Good morning, everybody. Idle time garbage collection scheduling. I'm Hannes Peyer from Google. I'm working, and this is joint work with my co-workers Ulm Dingbev, Jochen Eisinger, McElroy. Let me give you a brief. I'll tell you a few fun. I will give you a few fun facts about Chrome, in particular about the V8 garbage collector. Then I will introduce idle time garbage collection scheduling for improving. I will show in quite some experiments that this optimization really works. This optimization is shipped in Chrome since 1.5 years. In Chrome up there is using that optimization, which is really neat. About related work, this is not the first work where, and I will point out what the main contribution of our have a slide about conclusions. So, or scroll around and Chrome animates by 6 with everything looks smooth. What does it mean to? It means for each frame you have 16.66 milliseconds. All the animation work has to be done within 16 milliseconds. Everything works out okay. You have a smooth animation. It looks really nice. Animation takes longer than 16 milliseconds. Then you start. I'm pretty sure everybody in this room experienced that when watching a video or scrolling around on a web page. Become really annoying, and it may become really use this web page or this game anymore if that becomes really bad. But let's and see how Chrome works on a very high level. It works on the garbage collector. JavaScript is called the main thread in Chromium. It executes JavaScript, and this is used by Chrome. Very popular Node.js JavaScript framework. Changes the DOM, and when the changes to the DOM are done on the screen, and the component response, the compositor will look after every script and will draw the diff basically. Main thread in Chrome comes with a task scheduler, and this is basically a priority. Tasks get ordered by priority and executed in that order. Optimization work. We added basically you can have what I call like the that get only executed if nothing. We will use that later when I talk about on a very high level and a very simplified. Believe me, it is not that simple. You have the main thread. First, you get your input events, which can be network packets coming in. Then JavaScript based on these events. When this is done, the compositor then takes over, looks at the diff of the DOM, and eventually will draw. And if that all happens within 60 milliseconds, everything is to that picture later. Let's talk about V8 implements a generational garbage collector. The weak generational hypothesis that states V8 has a relatively small young generation, 16 megabytes big. This is where, and it has an old generation that can be increased, and objects that survive the young generation eventually get. If the weak generational hypothesis does not hold, we have an optimization. It's called figure out which objects are long living, but get it. So that optimization changed the allocation sites and objects directly at the AlBassam last year. Regular Chinese style semi-space garbage collector, contiguous memory, when the allocations collection triggers, objects that were newly are moved over to the other half of the semi-space. Space are promoted to the old generation. This works really well. Big generational hypothesis. If not many objects are surviving while going through the transitive closure, then scavenger operation is really fast. If not many are surviving, sorry. If many are surviving, it takes a really long time. So it's basically linear. What's important here, you cannot interrupt the scavenger operation. A young generation garbage collection, you have to finish its in state, and repairing that may be more expensive than finishing it. And performance rate. The second one is called full garbage. We have a pretty regular marking. We mark both through the old generation and meaning marking gets started on the main thread. Thread is paused. We perform a bit of marking on and so on until the whole transitive closure. We finalize the garbage collection cycle. Sweeper threads. This is performed completely concurrent. We also evacuate the young generation at that point, since we have the semi-space copy operation there, and we also compact our memories and compact some regions there. Generation. These are the most costly phases that may eventually lead to significant latency in the garbage collection. When does a full garbage collection get triggered? We don't grow all the way to 1.4 gig. We try to where the application fits in, and the limit a full garbage collection is derived from garbage collection times a factor that comes from a heuristic, actually. So for example, at a point in time, look at the live object size at that point in time, multiply it with time, which will be the next point in time where garbage collection. So if you look now garbage collection trace while browsing on a web page, like that from left to right, you will see like many scavengers, a lot of time. If you're lucky, they are 1 millisecond. They can take more. Copy them. At some point in time, you will see in time where you need to leave the main thread with the marking steps. It's happening in between incremental marking threads. You mark everything and you finalize your. What's nice about incremental marking that you really the API basically, I want to mark that many kilobyte of memory, or I want to mark until I reach that deadline. So this is really nice. You can scale up the marking steps arbitrarily. That will come in handy for our optimization later. And the finalization of the full garbage collection, on average on Windows computers out there, it takes on average 4 milliseconds, which is okay. But it may take longer if we decide that if the memory is really compacted and we have to do compaction, it may easily take longer than 1 frame, which could potentially be bad and result in dropped frames. Chrome is really a funky place for garbage collection, especially if you use it the way how I use it. You know, I usually have 1 tab open, which I'm really using, and I have like many dozens of other tabs open, and I keep them for whatever weird psychological reason, and I'm really never looking at them. So what matters for the foreground tab where I'm interacting with, where I'm maybe playing a game, their latency is really king, right? There I really want to have the smooth animations until the point where I just have the web page open and I'm looking at it, or maybe I walk away from my desk and do nothing. At that point, the tab actually becomes inactive, and I want to save on memory. I don't want to hold on to a lot of memory, right? And for background tabs, it's the opposite. The priorities are different. For background tabs, I actually want them to compress down as much as possible. But I want to be really careful there, right? I don't want to, when I switch tab, get a huge GC pause and wait for the tab to come up after a few seconds. Also, when I'm playing audio, I want to be really careful to identify an inactive tab and only compress these down when we think it's really inactive. So let's look into latency first. Let's come back to our picture from before. You have like your JavaScript there, the commit, everything works out great, but now you get one of these bad, evil garbage collection events in. The commit gets pushed a little to the right. It makes the compressor there start a little bit later. The draw event happens too late, and you miss a frame. Too bad. Garbage collection. And if that happens a lot on web page, users get unhappy. They talk to the developers of the web page. The developers get unhappy. The developers may be able to fix the problem. Then it's all great. But if they're not able to fix the problem, they approach us and ask us what to do. And typically, sometimes they come up with some really not so good ideas. And I call them the 3 deadly sins of garbage collection. And idea one is like, should I use object pooling, right? And please don't do that. That's basically explicit memory management on top of a GC. And you're going to defeat quite some compiler optimization. And you may end up with actually worse performance. Then a really fun one is, can I have an API to turn off the GC? I promise I will turn it on later when it's not latency critical anymore. No. So we really don't want that the programmers know about the garbage collector and interact with it. We don't want to do that. And most likely when your code base grows, you will forget to turn it on one branch and everything will be worse. And the third one, can I explicitly invoke the GC, right? Now is a time where I'm not doing anything latency critical. So if I would do GC now, I know later on I most likely will be fine. And that's also not a good idea. You actually don't know how long the garbage collection operation will take, how long, and the application does not have any notion of how frames get rendered and how much time is until the next frame get rendered. But actually, the idea is not too bad if you put it in the context of a trusted embedder. And this is basically the idea. Maybe Chrome is the guy who knows about idle times and when the next critical event will happen, and may cooperate with V8 to figure out if it's possible to execute garbage collection components within known idle time, and everything will work out great again. So if you look at that example here, where we miss a frame, where we miss frame 4 because a long garbage collection event happened. If we would have known in frame 2 that a garbage collection event will happen soon, and if we would have known in frame 2 that there is some idle time, we could have just performed it proactively in frame 2, and everything would have worked out great again, right? So that's the principal idea about scaling garbage collection proactively during idle time to avoid drop frames. So how do we do that? First, we have to figure out, is a garbage collection operation happening soon? And how V8 is doing that, it interrupts the execution of a program either on time or event-driven by allocations, and then checks, oh, is a young generation garbage collection event going to happen soon, or is an old full garbage collection going to happen soon? And if so, it will post a task to the task scheduler in Chromium, and we tell it, well, if you have some idle time, you may want to call me back sometime soon because I got some work to do. So step 2, the task scheduler will schedule idle task if there is idle time available. If there is no idle time, too bad. There is nothing we can do, right? This is a best effort system. This is has nothing to do with hard real time. We just try to do a good job here. Eventually, it will execute the idle task. It will invoke the callback, come back to V8. And V8 has then to do 2 things. First, it has to check if the event is still a valid event, or if it's an event from some time in the past, but there was no idle time and the garbage collection event happened already on the main thread, and it didn't work out. Okay, so be it, then nothing happens. But if it's still a valid event, V8 has to check like it gets a deadline from the task scheduler till what point it has to be done with garbage collection work, and then it has to compute, do I actually fit a garbage collection operation into this idle time? Will it work out? And if it looks like that it's not going to work out, it will not do anything. So for scheduling a young generation garbage collection, it's a really interesting problem. So you have this huge chunk of contiguous memory. You have some area bound pointer. The way how we interrupt the execution of JavaScript is every 512K of allocations, we go to the runtime and estimate, will we get another chance in the next frame to do a garbage collection, or will it be in this frame where garbage collection will happen? If that's the case, we have to schedule an idle task now that will call us back with the scavenger. Additionally, we are looking at heuristics like, do scavenger operations always take long for whatever reason? Maybe the hypothesis is not really working out, and with a really large scavenger operation, if they take more than 60 milliseconds, there's nothing we can do. So the second property there is like, it's kind of a growing strategy for a young generation, which tries to estimate based on the previous scavenging speed and on the actual size and on the average idle time we actually continuously get from the scheduler. It tries to proactively do a scavenge if it sees that a big enough young generation will result in longer pause times. For a full garbage collection, it's a little different. Incremental marking gets still started on the main thread at some point before reaching the heap limit. But as soon as it gets started, we start an idle task for incremental marking steps. And when the idle task with incremental marking steps comes back to V8, we can nicely scale up the incremental marking work to the given deadline we got from the task schedule. That's really nice. If it comes back with 8 milliseconds, we do 8 milliseconds of incremental marking work and make really, really fast marking progress during idle time, totally invisible to the user. And then eventually at some point we finish the whole transitive closure, or we're really close to that, and that's the point where we publish an idle task for finalizing the full garbage collection. And there we just take it turned out that looking at the past and looking at the average time of full garbage collections, if you take that into account and together with the current idle time, you can make a pretty good decision and prediction if it would work out okay or not. Okay, so much for latency. Let's look now into memory, and let's now look into one of these background tabs that are sitting there idle and not much is happening. And what you see there is like we had we computed heap limit prime for the next garbage collection to happen, and shortly after the last GC that computed limit prime, the tab moved to the background, not much allocation is going on, the growing graph is really slow, basically meaning we would reach limit prime after a few days, and we are holding on to a lot of memory, right? This is really bad, and if you have a lot of background tabs open, you will have a lot of background tabs that hold on to a lot of memory for no good reason. So what we do there is we try to detect if a tab is inactive. And we do that as in V8, which is not ideal because we don't really have a notion of being inactive. We just know, for example, the allocation rate. And if you think allocation rate is low, it looks quite inactive. And we also look at the JavaScript invocation rate from Chrome. And if this rate is also low, so if both rates, invocation rate and allocation rate are low, we think the tab is inactive. And if that's the case, we register a memory-reducing idle task with the task scheduler. We have a watchdog, basically, if like there's no interaction going on, a watchdog is going off every 8 seconds and checks these heuristics and publishes such an idle task in the task queue. The idle task scheduler is really nice for us. It also has a notion of idleness, of inactiveness. If nothing is going on, if there are no events in the task queue, it will give us up to 50 milliseconds of idle time. It turned out on the scheduling side, 50 milliseconds is kind of good enough. If you go away for 50 milliseconds and input events are coming in exactly that time, it will work out fine from a user experience point of view. And with 50 milliseconds of idle time, we can do quite some incremental marking work to finish a memory-reducing garbage collection operation fast. Let's look into some experiments. So in the paper, we used Chrome stable channel 48, is basically February this year. We run the experiments on a Linux workstation and on mobile devices. The slides I just have the results for the Linux workstation. On mobile, you will have less idle time because CPUs are slower. On the other hand, web pages are also a bit more lightweight, but in the benchmarks we're using here, you have about 50% less idle time. So if you cannot take that much advantage of it, and it's about 2x less improvement on mobile on the benchmarks we're using here. We're using the Chrome telemetry performance benchmarking framework to run our experiments. This is really awesome. So what you can do with telemetry is you can point it to Facebook and say, Facebook, scroll down for 60 seconds, and you record this trace, and you can replay it as many times as you want. So this is really a nice way of generating a lot of real-world web pages. And you can do even more complicated stuff than scrolling. You can click around and write messages. And funny enough, our optimizations landed on tip of tree. So our baseline is we have to turn on the idle tasks. And we run each benchmark 20 times to get like a good stable results. The first one is a WebGL-based game or online. Just point your browser to that URL. And here the improvements on the first metric, and this is a metric we actually introduced in the paper. I had no time in my talk to go into details there. Please check it out in the paper. We call the metric frame time discrepancy, and it measures the duration of the worst irregularity in frame rate. And we think that really correlates nicely with user experience. And the improvement on that metric is about 35%. If you look into frame rate, which is like the traditional metric for user experience, there's not a huge improvement there. But it's also kind of obvious. If you render 1 million frames, like not in every other frame garbage collection is happening, right? It's a pretty rare event. So if you improve a little on garbage collection, it will not have a huge impact on frame rate. But from a user experience, it is significant. This is also a motivation behind this metric, which really tries to get that. A lower level metric is missed frames due to GC. We also looked at how many frames get dropped because of GC and what's the improvement there. And that improvement is quite significant. It's more than 40%, and it also correlates with frame time discrepancy well, which is a good thing. But not everything improves, like low is better here, right? What gets worse is the total GC time increases here by 12%, and this is because we proactively do garbage collection, so you will end up with more garbage collection work in the end. But if user experience gets better, well, so be it. Another set of benchmarks we used with the telemetry framework, it's what we call the infinite scrolling web pages. We took a bunch of interesting websites like Facebook and Twitter, opened them, and then started basically the measurement and scrolled for 60 seconds. And what you see here in the graph is like how much of the total garbage collection work is performed during idle time. For some web pages like ESPN, it works really well. For Facebook, it's 80%. Garbage collection work performed during idle time and not missing before the deadline. Overall, 50% to see because of idle time garbage collection scheduling events bad, and in this one a little bit more garbage. One full garbage collection happens more in the trace contribution. This effect becomes less visible. Google Search on the right, Google Docs. Google Search being active, so you're not touching anything. You see the baseline is just staying up. You're not reaching the limit soon enough. Really fast and trimming it down to something small. And for Google Docs, it's interesting. Google Docs also, when it's active, it's doing a little bit of allocations, so you eventually run into garbage collections, but it's slower, and the curve is staying kind of a constant from each other. Related work, well, as I mentioned, we are not the first group working on scheduling garbage collection during idle time. There's been quite some work in the past about, mostly in the context of hard real-time systems that schedule garbage collection periodically, also kind of related to our work. Slack-based, meaning, well, as soon as idle time, the garbage collector schedule such a task, or doing it hybrid, which was found to be superior. of these systems. The main contribution of our work really is that we try to estimate how long components will take in given idle time for a scheduler via it, what maybe other systems are doing. And we're trying to keep the high throughput garbage collector what we have and try to get the latency improvement by taking advantage. How does it relate to concurrent, parallel, and incremental garbage? Marking really nicely integrated into our system. Currently, well, you may be better off, but on the other hand, throughput may tank, especially when it comes to concurrent. Quite some, which usually introduces quite some performance write or read barriers. All right, let me conclude my talk. Idle time garbage collection may improve responsiveness of and memory consumption of web pages nicely. We demonstrate that in the wild. We also have data from real-world users where we measure on our performance channels that this works really great. And the nice thing was we did not change the garbage collector, right? We did not implement a real-time or soft real-time garbage collector to improve latency. We didn't touch the code base at all there. We just built on top of the garbage collector, trigger different events if we think that it may work out. All this stuff is shipped in Chrome, so if you're browsing right now the web, you're using that. We had introduced a new metric in the paper, frame time discrepancy. Unfortunately, no time to talk about this one in my talk, but check out the paper. It works really nice, especially with games or animations that require 60 frames per second. Applicability, well, we think it's totally virtual machines like on Android and Arc, which have a context of screen rendering. On idle time, I would think that they. And I also think, like, you know, Node.js is used with the idle time infrastructure. So maybe also on servers where you're not under 100% load, you could take advantage of idle time and just call our APIs and hide your garbage collection time during idle. Thanks.
So you said that 5% of your idle tasks overshot their deadline.
Yeah.
My assumption is that the marking tasks are almost perfectly precise because you can just stop that whenever you want.
Yes.
So do you have any information or insights about predicting pause time for the more complicated operations like compaction?
So it usually depends on how homogeneous the application behaves. So like predicting scavenging works really well if the application has is doing the same actions over and over again. So that also works out really well. For estimating the time of finalizing a full garbage collection, this is the event where we got most of the frames missed because there we don't have really a linear dependency. We know like compaction, okay, will be kind of linear, but this one is really hard to predict. So we take the average there and add some constants to be like really conservative, but we thought like this fully finalization events mostly contribute to the overrun. And I think you could maybe do a better job with fine-tuning there. Yeah.
Thank you.
Hi, Manu Sridharan, Samsung Research. So you had statistics saying you were reducing dropped frames by, I don't know, 50, 55%. Do you have any idea for the remaining dropped frames, how many are due still to the garbage collector as opposed to, I don't know, just some issue in the application or other parts of the browser?
Yeah, so these are just data on dropped frames because of garbage collection. So the other frames are still because of garbage collection. The reasons maybe are because there is no idle time. We don't always have idle time, and so they're happening on the main thread. And yeah, or they overshoot and then contribute to the drop frame.
Okay, thanks.